this strong interaction limit is somehow interesting and quite unique because it sits right at the interface between quantum chemistry methods, wave function methods, and hybrid methods where instead of making a sparse ansatz for a full system, you remodel the system to lower the complexity, in this case DFT. And so I begin with a comment, taking up a comment Alex made yesterday in the inaugural talk. So Alex, you were saying that we haven't progressed all that much on really solving high-dimensional problems. So I completely agree with that. So it's still a big challenge, and also ongoing work is interesting in this area, like pushing the dimension of the problems we can actually solve accurately. So now I begin with a couple of comments before I get into sort of technical details on this limit. So it's a low density limit of the exact functional, of the exact density functional associated with the uniform coordinate scaling, where you send rho of r to lambda cubed rho of lambda r. So that's just the particle number preserving uniform scaling of the density. And so when you do this, you kind of get insight into the interaction energy directly from the density. And so one of the things that really got me interested in this is that none of the ingredients from the usual Jacob's ladder of DFT appear in this limit. So you see neither the local density nor density gradients, nor the KS kinetic energy density, nor Hartree-Fock exchange, nor virtual orbitals. But instead, what you see is long-range correlations that are not governed by higher derivatives, but by integral constraints. So the physics of this, I will of course explain. It's strictly correlated electrons, strict correlations in the positions, and in maths that leads into the field of optimal transport theory. And so now, and actually, so the limiting Hartree exchange correlation functional in this limit is called the SCE functional for strictly correlated electrons. It can be integrated into Kohn-Sham DFT. So you can do something with really pretty accurate, strong correlations without leaving this beautiful realm of Kohn-Sham DFT. And now, of course, as with all asymptotic limits, it's not reached in nature, okay? But the KS-SCE, I should say, it does capture some important physics of some strongly correlated molecules, which is missed by semi-local or even by hybrid functionals. So I give you an example. So that's the H2 molecule in the dissociation limit. So the black curve is the truth, so full quantum mechanics. The blue curve is the LDA, and the red curve is Kohn-Sham with the SCE functional, KS-SCE. So now you see that near equilibrium there is a disastrous, excuse me, maybe I think I should really, no, this damn thing, I think I stop using it. Okay, so we have quite disastrous underestimation of the energy here, but at really long range, it actually gets very good, and it gets the dissociation limit exact, and that's a tough challenge for DFTs to get this dissociation correct, and all the standard functionals kind of fail it. So what's the explanation? I mean, very roughly, when you pull the atoms apart, at least there is some region where the density gets small. It's not low density everywhere, but there's some region where the density is small, and that's actually a large region. So the correlation is not mediated by a uniform electron gas of constant density, but the interaction is mediated by a dip of very low density. And then, even though the scaling is far from the scaling limit I showed you, nevertheless, it gets the physics kind of right here. When you're near equilibrium, assuming this inhomogeneous low density scaling is a disaster, you're much better off taking the opposite limit, and that's somehow, and the KS, the standard LDR is close to the opposite limit and gets this much better. Okay, so here we go. So now I want to, so after this intro that hopefully gets you a little bit interested, I want to structure my talk in 3 parts. I do a bit of background on the strong interaction limit, then I talk about discretization, and then I present our algorithm. And so all this stuff here is, we recently wrote a comprehensive review. That's myself, Augusto Gerolin, and Paolo Gori-Giorgi. So that's out on Archive and will appear in a Springer volume on DFT, which Eric Cancès and I have been editing. Thanks to everybody in the audience who contributed, and apologies for the long time it took to process all this. But like all the articles in this volume, it's written for a broad audience, hopefully appealing to physicists, chemists, and mathematicians. Okay, so here we go. So background on the strong interaction limit. I start with the derivation of the SCE functional. So the derivation is quite simple. You start from the exact Levy-Lieb functional. So that means you minimize kinetic plus interaction energy subject to a given density. And so for the few people in the audience not working on this, here the formula for the operators, then you do the uniform coordinate scaling, and then you discover that the kinetic and the interaction energy scale differently. So because here you take a Laplacian, it's like 2 derivatives, you divide twice by a length scale, so that gives you a factor lambda squared. With a Coulomb repulsion, you divide by 1 length scale, which is the inter-electron distance, so you get a factor lambda, and so then you need to minimize this thing. So it's exactly the same scaling everybody knows from first-year quantum mechanics when you derive the virial theorem. Yeah, so at the minimum, it needs to be a minimum with respect to this rescaling, and that gives you the, differentiating this with respect to lambda, gives you the virial theorem. Okay, so now now that the scaling is different, when you make lambda large, the lambda wins, and sorry, the lambda squared wins, and yeah, I'm so used to the lambda winning. But when lambda is large, the lambda squared wins, okay? So the square of a large number is even larger than the large number, okay? So then the kinetic energy dominates, and then you get this approximation for the exact functional. It's roughly lambda squared times just minimizing the kinetic energy under given density. And at low density, the interaction energy dominates. So if you square a small number, it gets even smaller. So then the interaction dominates, and you get lambda times this. And so here is the definition of the SCE functional. It's this term here, cleared of the scale factor, and it's just the analog for interaction of this term here, which is just the Kohn-Sham kinetic energy functional. Okay, so SCE functional is just the analog of the standard Kohn-Sham kinetic energy, but for interaction. Okay, so here we go. That's the derivation. Now, the way to add that in SCE into Kohn-Sham, so the simplest and most primitive way to do that is just to estimate, just to add the 2 functionals. So use this as the Hartree exchange correlation functional. Of course, that neglects that when you are supposed to minimize the sum of 2 terms, you can't minimize them separately. So that's an underestimation. But it's a useful first approximation introduced by Marley and Gori-Giorgi in 2012 in PRL. And so then you get familiar Kohn-Sham equations where the effective potential is just the functional derivative of the SCE with respect to the density. Yeah, I realize I should have used a stronger font here of the stuff I wanted to underemphasize, but okay. Here we go. So it's functional derivative with respect to the density, and so then the usual constraint. So I'm writing down here the closed shell case for simplicity. So twice sum squared of the orbitals, and so part of the challenge then is when you want to implement this, you need a way of computing this potential. And And in particular, I'll get back to that. And of course, this is a primitive approximation. There are much better combinations of SCE with Kohn-Sham, but this is ongoing research. I won't have time to discuss this here, but if you read our review, we discuss it there. Okay, so now what's next? I wanted to show a picture what this constrained search wave function looks like. So I've cleared an overall scale factor, and then I minimized t plus 1 over lambda interaction energy over the given density. So when you do that, you see a crossover. So what I'm plotting here is the pair density, so wave function squared, and integrate everything out except 2 spatial coordinates. And so here you are in the high density or weak interaction limit. So you get sort of standard exchange type correlations where just the density is depleted on the diagonal. So that's this exchange correlations. And then there's a slow crossover, and some very interesting multiscale structure develops. So I should mention multiscale since it's in the title of the workshop. So here's a multiscale structure, okay. And so when you go to the, really to the extreme limit, lambda equals 0, so interaction fully dominates, then the pair density concentrates on lower dimensional sets. So we will see more of that. And so that was a simulation we did in 2015 with Wajie Chen, and was done with FCI. So finite elements are good because they, so localized finite elements are good because they diagonalize the VEE. Yeah, so if you have a kinetic energy dominated regime, you rather want to use something like plane waves or something like this because they would diagonalize the T. But here it's good to go into spatially localized FEM. Okay, and plus some quasi-Newton for the constraints. So we made sure we accurately solve. So that's the picture here. So what we learn is, so the correlations are completely different depending on this on the scale parameter, so on the density profile, whether it's dilute or concentrated. And in the limit we get some really interesting sparsity. Okay, so next slide, I want to talk more about the sparsity. So sparsity always has to do with the representation you use. Okay, so in the high density regime, you get some sparsity which is kind of implicit in the Kohn-Sham choice of separating out the Kohn-Sham kinetic energy among other terms. So that was a very ingenious choice, and it's partially based on the belief that the non-interacting limit is not so bad an approximation, at least for the kinematics of the fictitious KS orbitals. So you expect, and so this would become more mathematical in the high density weak interaction limit, because then you have a non-interacting system, and then the limit of the wave function, in the limit the wave function becomes just a Slater determinant. So for non-interacting systems, Slater determinants are an exact ansatz. Okay, so everybody knows that, and so the parameters here would just be n Kohn-Sham orbitals. And so now let's discuss complexity. So there are two types of complexity. One is the data or storage complexity. The other is the algorithmic complexity. At the moment, I'm just talking about the data complexity. And so that goes just linear in the number of electrons and linear in the number of single particle basis functions. So that's the data complexity. You have n orbitals, and if you use L basis functions for each, you get n times L. So that's a linear scaling in both parameters, so that's kind of as good as it gets. Now let's go in the low density. So if you do now an expansion in Slater determinants and look at the full CI expansion, it's extremely highly non-sparse. Yeah, so you get exponentially many important contributions. So it's not a good idea to use this representation, but Mike Seidel, who was the first to introduce and study this limit, he made the following beautiful observation. He said, well, I believe or hope or suggest that the limit of the sum over the spins of the wave function squared has a sparse structure, but a completely different one. So you get a symmetrization of something, namely its density, the given density in the first coordinate times a bunch of delta functions in the other coordinates. So whenever you know the first coordinate, Mike Seidel says, then the position of the second electron and so on, and of the nth electron is fixed, given the first electron. So these are long-range position correlations that emerged, and really strict correlations in the sense of a delta function. So there's a unique position, and why sum over spins wave function squared? Well, if you look at the expected value here, if the kinetic energy is gone, you find out that the interaction energy only depends on this quantity here. So you cannot hope that any other stuff also converges. So that's kind of the minimal information you need to evaluate this, and that's the thing that should be driven by minimizing it. So therefore, one should look for an asymptotic limit for that. Okay, and so now let's do the data complexity thing here. So you have n co-motion functions, or these are maps from R3 to R3, describing strict long-range position correlations, non-local correlations, strict in position. And so the data complexity, if the ansatz is justified, would again be n times L. Why? Well, if you discretize the density by n grid points, so the one-body space by n grid points, so to speak, you go in a delta function basis in position space, you get the factor L, and then you just have n maps here, or more precisely n minus 1. So you again get this beautiful low data complexity, but in a completely different representation. So we'll talk more about the answers later. And now I want to, next slide is I want to talk about the correct formulation of the limit problem. And also it has a nice mathematical interpretation connecting to optimal transport theory, which is an area which became fashionable lately. But it's an immense pleasure to see somewhere in the back. Yeah, with this mask, I can't see Wilfried Gangbo. Wilfried, oh, you're hiding in the back. Yeah, I don't recognize you with a mask, but he's one of the pioneers of this theory. And in fact, he was at Carnegie Mellon in the early 90s when I was a postdoc, and he was the only one working on optimal transport. And we all thought Wilfried is crazy. I mean, it's a beautiful problem, but it will not be of any good in the future. And so we said, no, we work on our stuff, you work on your stuff. And then, yeah, now I'm a wiser man. So Wilfried was a wiser man 20 years early. Okay, so here we go. So the correct formulation then is to minimize the integral of the interaction energy, not against wave function squared, but really over n-body probability measures with a given one-body marginal or one-body density. And so that's the correct formulation. Why? Because when you stick with wave functions, square integral wave functions, and try to minimize this thing, then there is no minimizer. Yeah, I showed you how this concentrates on, I mean, you have delta functions. So there is no square integrable function whose square is a delta function. That's not possible. Okay, and so, so that's the correct formulation. You need to extend the setting to n-body probability measures with given one-body marginal was introduced independently by Gudina Kotzar, myself, Claudia Kluppelberg, and Butazzo, De Pascale, and Paola Gori-Giorgi. And so then there is a theorem that we proved. It took us a while to prove this. So the minimum value of this over these n-body probability measures is still the SCE functional. Yeah, it's the same as taking the infimum over the square integral wave functions. And so that was in part motivated by a nice article by Seidel, Gori-Giorgi, and Andreas Savin, who is also in the audience, because they are yeah, Andreas, we should appoint you an honorary mathematician or something, unless you're embarrassed by this title and want to hide it. So because Andreas said, well, you know, actually it's not even that clear whether one can drop here the representability and sort of really, you know, whether if one minimizes somehow like this, whether that gives the same, somehow first passing to the limit, to the coupling constant limit, and then do the constraint search, or do it the other way around. And of course, sometimes in mathematics, these things don't commute. I mean, we took the trouble in our paper here to write out a didactic example. If the functional one was looking at in the Levy-Lieb constraint search contained if the constraint also contained density gradients, then this thing wouldn't commute and you would get an extra term. Okay, but here it works just fine. Okay, so, but you know, it's great if people like Andreas raise these questions in their physics papers, because then I could understand that paper a lot better than Mike Seidel's paper. So now let's go to optimal transport. So that's a more general setup. So there, in general, you find you want to find a multivariate probability measure which optimizes some cost subject to the constraint of given univariate marginals. So integrate over some cross space RD cross parabola cross RD some cost against some probability measure, and the marginal condition means, I've written it out here for endpoint densities. So the ith marginal of the ith coordinate means you take the endpoint density and integrate out all other coordinates, denoted here by xi hat. Okay, and then optimizers are called Kantorovich plans. So now there's classical optimal transport. There you have just two marginals and typically a distance cost, x1 minus x2 to the power p, where p is bigger or equal to 1. I have a picture later, so this came from moving a given pile of shape mu1 efficiently into a given hole of shape mu2, and was motivated by civil engineering. I have a picture on the next slide. The second example is a so-called Wasserstein barycenter, so it's important in data science, and so the marginals then are given probability measures, for example, images or data sets, and you want to find a representative summary of these data sets. That's an object called the Wasserstein barycenter. It also leads to this problem. And then the third example was a strong interaction limit. Then here you get a Coulomb cost, and all the marginals are equal. Okay, so let's. I did a picture for classical OT here. So you're minimizing this x minus y to the p cost introduced by Kantorovich 1942. The optimal gamma is called a transport plan. So Kantorovich lived in the Soviet Union. So in those days there was a planning economy. So these were really producers and suppliers. And then the optimal cost in this case is the Wasserstein distance between the two marginals. And so one way to put the connection, so if you want a catchy one-liner that tells you how strictly correlated electrons connect to the Wasserstein distance, it's the following. So the SCE functional is precisely the Coulomb analog of the Wasserstein distance. Okay, so you just replace the p here, the positive power by a -1. Okay, and then you get the SCE functional. Okay, so and then the version by Monge. So Monge, so he lived under. So he was a protege of Napoleon. So in those days, they were also doing significant planning, but it wasn't that centralized yet. So it was a problem motivated by civil engineering. So you move a pile of sand or mortar on a construction site into a given hole, minimizing the transport distance. Okay, and so then the second marginal condition is a little complicated. I don't want to discuss it here. And so then there is a celebrated result by Jan Brenier in the case p equals 2, and by Wilfried in the back and Robert McCann from '96, that the optimizer is unique. and precisely satisfies this Monge type ansatz here. So every point is just moved to one other point. And so now here comes an interesting fact. So the Monge ansatz is precisely the same as the Seidel ansatz. So what Seidel did is he rediscovered Monge, more than 200 years later, in a completely different context without being aware of the connection. Okay, so that's a very nice coincidence. So these things sometimes happen. So good scientists from different corners come up with the same ideas. Okay, so so the result then, I stay here in the simplest case for the quadratic cost. It is a kind of sparsity result. So a priori you're allowed to map every point to a diffuse distribution. So the support of the optimal plan might look like this. So it might be a 2D object here in this drawing, but in fact it's a 1D object. So it's just each point gets mapped to one other point. Okay, so now then let's go to the Wasserstein barycenter. So let's first start with why one is interested in it. So it's typically a much better summary of a bunch of data sets than taking the linear average. So I've plotted here an example. If I take two Gaussians, the green one and the blue one, if you take the linear average, you get kind of two peaks, yeah, at both the positions. But every statistician would tell you that is terrible. That's a terrible summary of the data. You might just have a change in standard deviation and mean. And indeed, so the Wasserstein barycenter is this guy here. And in fact, it automatically generates the Gaussian with the arithmetically averaged mean and the arithmetically averaged standard deviation. Okay. So that's the Wasserstein barycenter. And the way you find it is you minimize this cost here. So again, it's an optimal transport problem, multi-marginal. The marginals are the given data sets. And so then, and then you do a push forward of the optimal plan by the barycenter map, so to speak. So this map is made in such a way that if your marginals were n delta functions sitting at different points, you would just get the delta function at the classical barycenter. Okay, and then just kind of by superposition, you kind of have to define it this way, if you think about it. Okay, so yeah, here we go. That's the Wasserstein barycenter. And again, so in this case, so again, the Monge ansatz equals Seidel, and these people, yeah, and it's actually a theorem that again you get the sparsity. So now for the strong interaction limit of DFT. So when we first started thinking about it, we thought, oh yeah, sure, it's going to be true for Coulomb. But the world is not nice to us in this case, so it's not sure whether it's true for Coulomb, so it's still open. Nobody knows whether this Monge / Seidel ansatz is true for Coulomb. So, and in fact, so they're non-Coulombic counterexamples as soon as you have either 3 or more marginals or the space dimension is bigger or equal to 1. So, but in the case when you have only 2 marginals in n dimensions or n marginals in 1 dimension, it's a theorem. So that tells you the question is subtle. Yeah, okay, so I mean it's always true in 1 dimension, always true for 2 electrons, but there are non-Coulombic counterexamples once you leave this realm, and Coulomb itself is not known. Okay, so yeah, this and so an example. So I give you an example, a special case of the physics of the Seidel ansatz. So when you believe in, if you believe in Wigner crystallization, which I guess we all do. I mean, nobody has proved it, but we believe in it. So when you go in a homogeneous electron gas to a very low density, what is expected to happen is that the electrons, they form superpositions of translates of a crystal lattice. So the first electron will somehow be at a position that varies according to the given density, and the other electrons are translated along. So it's a kind of a resonance state between different translates of crystal lattices. Okay, and of course a highly correlated state, because in the case of the uniform density, all these configurations have the same weight. So So yeah, so that would be what this would look like. So now in 1D, I just want to show you the exact solution. So you can find these Seidel maps by the following construction. So that's from Seidel's paper. So you just make sure the distance between each map and the next map, when you integrate the density in between them, you get the area equal to exactly 1 electron. So all particles are 1 electron apart, but 1 electron in terms of the density that sits in between them. So that means when the density is low, they're very far apart, because you need to go far apart to reach, to transverse the density of 1 electron. At high density, they're very close in Euclidean distance, because you need to traverse only a small distance to accumulate a total density of 1 underneath. Okay, so that's his construction.
Can I ask a question, Gero?
Yeah, please.
In the previous slide,
yeah.
the minimization problem, how does the gamma take the anti-symmetry into account?
Ah, okay, yeah, yeah. Yeah, okay, so yeah, then maybe I was too quick on the slide on Andreas's question in the paper. So you know, so it's basically, so the answer is, how does it take it into account? It doesn't, and it doesn't need to. So you can minimize over arbitrary probability measures here, even though they are not representable as squares of an antisymmetric wave function with spin. But you can cook up a fictitious antisymmetric wave function with spin, which gives a square which is kind of sufficiently close in some kind of, you know, weak star sense that is enough to converge this integral. And so, but actually constructing this approximation took us a long time as a bit of work. But and so roughly this comes from, you know, okay, so it really comes from the kinetic energy missing. If you have the kinetic energy missing you cannot do that. But here there's kind of no penalty for making the, yeah, for inserting some nodes somewhere. There's only negligible penalty. Does that make sense? Okay. Okay, so yeah, let's yeah, but great question. Okay, so yeah, now we went through this optimal transport stuff and the Seidel solution. Now I come to discretization. Okay, so the discretization is really, yeah, if you discretize the single particle space by L grid points, then the structure is just, so you just get a linear program. So you minimize a sum of coefficients times the coefficients of a probability density on lattice, and just you have a non-negativity constraint, because probability measures are pointwise non-negative, and you have the marginal constraint, which is a bunch of linear constraints. So it's just a linear program, but the trouble is the cursive dimension. So the system size blows up exponentially, as we've seen, you know, many times in talks already, even though we're just in day 2, and I'm sure there are further examples coming in coming days. Okay, so it's just a linear program, but it's really high dimension. Now, but there is a rigorous sparsity theorem, which we worked out in 2018, myself and Daniela Voegler. And so it's the following. So the extreme points of the convex polytope of admissible endpoint probability measures, or order n tensors, so these are tensors with n indices. So the extreme points of this convex set, they can be written as convex superpositions of at most L pure configurations, i.e. symmetrized Diracs. So it's really a sort of nice fact from convex geometry that the extreme points are not that complicated. So a pure configuration is a product of delta functions symmetrized, means for each electron has one definite position, so no smearing out. And so proof by convex geometry, the offshot is you have an exact ansatz with sort of L times n plus 1 parameters, because you have, yeah, I mean, you just have to count the parameters here roughly, and then it's and there's a subtle thing. So we tried for a very long time to prove that this Seidel-Monge ansatz is correct, but it's actually not correct. Also not in the discrete case. Okay, so it's incorrect, and I worked out a counterexample. It's a paper in 2018. I don't cite here, and so here's the difference. So it's a very subtle difference. So you take basically it's the same ansatz with the product of delta functions, but the prefactor is not the density. But you need to relax that and allow a general one-point probability measure. Okay, and that's also why you get the n+1 here, because you get an additional L degrees of freedom for this probability measure if you have an L-point grid. So it's very easy to write down, but it took us a long time to find. And I don't think you would come up with this just by waking up in the morning. You come up with it by studying systematically the convex geometry of this polytope of admissible tensors and determining the extreme points, and then you see it has this meaning which is quite close to Seidel. So at the end we were quite happy because we proved something that is kind of close to what Mike Seidel wanted. Okay, so now there's also a dual problem, like with all linear programs, there's a dual program. So in the primal program, you have many unknowns but few constraints. In the dual is the other way around. You have only a few constraints, but zillions of, a few unknowns, but zillions of constraints. So it shifts the curse of dimension to the constraint. But the value of primal and dual agree by linear program duality. And so I think the nicest aspect of the convex duality here is that it gives you the SCE potential. So the optimizer of the dual problem gives you a rigorous definition of the SCE potential. It's just the optimizer on the dual, and you can prove it exists. I mean, for mathematicians don't like functional differentiation of indirectly defined objects because you never know, under what conditions are the functional. But I mean, that's a rigorous definition, and it agrees with the SCE potential. Okay, so you can construct it this way. And so now I come to numerical methods. So previous methods. So yeah, there are lots of methods. I hope I didn't leave anyone important out who's in the audience here. So yeah, Seidel, Gori, Georgi, Savin worked out the SCE state and potential for the radial, for radially symmetric atoms, not all atoms, but the radial atoms from helium to neon. So using radial symmetry and the Seidel ansatz, then our one of our main conference organizers, Lin, is he somewhere? Yeah, no, maybe he's. Can we see Lin? Oh, there he is. Yeah, I recognize no one with these masks. So okay, yeah, Lin did a nice work using the dual formulation and a few parameter representation of the effective potential. And then myself with Wajid Chen and Chris Mendel, we worked out the H2 molecules with adaptive FEM and linear programming. I showed you the resulting KS-SCE potential energy curve. Then there's a standard algorithm in optimal transfer called Zincon algorithm. So it's based on a kind of entropic regularization. So you introduce a small amount of fictitious temperature. And so then they worked this out for the lithium atom. And then Yuhao Ku, who's also in the audience somewhere with Lexing Ying, they had a very nice algorithm by semi-definite relaxation of a two-point marginal formulation by us. So we gave an exact reformulation by two-point marginals, and they found a very efficient approximation, which is computationally much simpler and could push it to kind of 10 electrons. Then there's also very recent methods by Alfonsi, Coyot, Erlacher, and Lombardi. So they have yet another approach. They say, okay, we discretize only the marginal constraint, but keep the state space continuous, and then we try to. Then it becomes a high-dimensional function optimization problem on a manifold, and then they try to do this by a stochastic particle method. Okay, so now I get to the new algorithm. So this is what we did. So this new algorithm is based on 3 ideas. So the first one is to exploit the extreme sparsity of optimizers. So in particular, this discrete version for multi-marginal of the old sparsity results that we did, which is minimally more general ansatz, but always works, it rigorously breaks the cursor dimension for storage. So it suggests a natural but highly nonlinear manifold on which to run simulations, by exploiting this. And so, for example, the sinkhorn, which is the standard computational method in optimal transport, it will never work in high dimension. I mean, people are trying, but it will not work. No matter how hard they try, because it's based on smoothing the transport plan out, and thereby in low dimension you can afford this, in high dimension you cannot, because you switch on an exponentially large amount of extra coefficients that should be 0. Okay, so in it's not a high dimensional method. It's good in low dimensions. It will never work in high dimension. Then we bring to bear a method from integer programming, so called column generation. So it's well established in integer programming and has not played a role in optimal transport before. Then comes the last point. So that's maybe the most difficult one. So we decided not to model the unknown intricate correlation structure. In particular, we went away from the very detailed ansatz with both Seidel's ansatz and also our minimal, slightly more general ansatz. We love our ansatz, but we threw it out because we chucked it out because the maps have jumps across codimension 1 surfaces, and when you go into map and try to do that computation, you throw it out. Don't try to model the correlations. Make no ansatz, just learn it. Okay, and so we are talking here not about database learning, supervised learning, but we have to do unsupervised learning because we wanted to do ab initio, just solve the equation. Yeah, so it's not data-driven learning, it's unsupervised learning. And then what you then got to do is you have to learn with an adversary. And in this case, natural adversary suggests itself as the dual state within column generation. And so this was loosely inspired by the recent concept of Wasserstein generative adversarial networks by Arjovsky et al. 2017. Okay, so use an adversary. Remember AlphaGo, right? I mean, how did AlphaGo beat humans? By learning from the adversary, which in this case is itself. Okay. So here's the algorithm. Yeah, so that's somehow my picture. Yeah, it took me a long time to do this picture because I was giving talks about this algorithm last year and nobody understood the algorithm. Now I had a long flight to LA, so then I had time to do this slide. So, okay, so here's the idea. So you alternate between solving the strongly interacting limit problem on a small but otherwise unconstrained subset of the n-body configuration space and updating the subset. So here is the subset that's called omega. That's n-body configuration space, 2 copies of the grid, and so the 1-body configuration space is L grid points, and we keep the active space bounded by a constant times the number of marginals. So the theory tells us we could use beta equals 1, but beta is a hyperparameter. It's better to make the set slightly bigger. So we thickened it up, but just by a linear factor in all our simulations, the hyperparameter was 5, independent of the dimension. I show you simulations with up to 30 marginals. This is always just 5. Okay, and so then you initialize at random the set in the big space, then you solve the strongly interacting limit problem on the subset. Okay, and then it's a small linear program. You get the primal solution, which is an n-body density, but on a small set, and you get the dual solution, the potential. Now then, so that's your update of the primal and dual. Now you need to update the set. So that's the subtle thing. So you do it as follows. It's kind of genetic learning method. Pick a random parent configuration, but don't pick it randomly in the set. Learn from the optimizer that you currently have. So only a small number of these cells here have non-zero weight in the optimal plan. And so that's a crucial information that tells you something about many-body correlations. So you only allow configurations to be parents on which the current optimal plan is positive. And by the theory, there are only L of them, but you have 5 times L. So you really learn, you kill 4/5 and you keep only the good ones. So, and then these guys can create children by moving 1 electron to a nearest neighbor. So that, like the small icon should be a human and this should be a baby. I'm not sure yet. Maybe I should have done the drawing a bit larger. Okay, so maybe you can see it better online. So the successful configurations, i.e. parents, so they can create a child by moving one of the 2 particles by 1 lattice side. Yeah, so if it's R1 prime, R2 prime, one of these coordinates can hop to a nearest neighbor side. Okay, and so now then you don't accept every children, but you have an acceptance criterion. So for the acceptance criterion, you use the current dual solution. And it's a very simple evaluation criterion. You evaluate the cost of this new configuration. So it's just a pair potential evaluator. It's very, very cheap. I mean, it would be Chris's dream if everything was as cheap as this, right? Christoph, yeah, you were worried about the 5-body or n-body. So it's just 2-body. Evaluate this minus this sum and check whether it's positive or negative. If it's positive, you go back and pick another one, another random parent and another random child. If it's negative, so if it's fulfilled here, then you accept the child and you update the active configurations. You add this to the active set. And then occasionally you clear out the oldest unused configurations to keep the overall size small. Okay, and so, sorry, yes, please.
So it's maybe obvious, I'm sorry if it is. Why do you only go to neighbors?
Oh,
create new electrons?
Well, cheapness, it's not essential, but it's essential that you don't hop to an arbitrary configuration, because I mean, if you just do a random hop of the whole configuration, then if you do a random hop of the whole configuration, you have too many choices and it wouldn't work. You get back into the cursive dimension.
But is there a reason that making too large hops?
I mean, okay, so the reason is empirical, I show you, because it works. You don't need to do more.
That's fine.
I would have thought that this would take into account the line structure, I mean the codimension 1 structure.
Well, it's kind of, I think of it differently. It's like a gradient descent. I mean, just the nearest neighbors. I mean, it's something like a local gradient. Okay, so here we go. So then, and so the acceptance criterion, so this looks a bit funny, but it's computationally easy, but here's the meaning. Acceptance criterion is true if and only if the current dual state, so notice the dual state is always a function on the whole, on the whole grid, but it's just on the 1-body grid. So the acceptance criterion is true if and only if the current dual would no longer be optimal if you add this extra point into the active set, into the set on which you solved it. So that's, that's the criterion you should put, right? Okay, and so that's computationally very simple. More later, so here's some other comments. So this breaks the cursive dimension for storage here, already discusses and still captures the exact solution. And then another comment is kind of on this one, okay, really only the successful configurations can bear offspring because of this condition here. So that's a sort of genetic aspect. Okay, so that's the algorithm. Let's skip other justification. Yeah, okay, I want to skip this and want to show you that it really works. So this algorithm works. So let's start with n equals 10, L equals 100. So number of unknowns is not that big, but it's nice to plot here. So so I visualize the primal state by the pair density and the dual state by I can just plot it here. I took just some lump as a density, doesn't matter what you take. And so here's what happens. So here's like after 500 iterations, you get a little bit of depletion on the diagonal because there's a Coulomb repulsion, so electrons don't like each other. The dual state looks pretty random. After 2,000 iterations, it already looks quite nice, and there's some structure. And so here we go. So after 5,000 iterations, you already see a pattern similar to the Seidel maps and a nice potential. And after 7,000 iterations, you got the exact solution. So in this case, in 1D, you have the exact solution. It's the Seidel maps, and that's the Kantorovich potential. So we got it to machine precision. So here's a sort of cost minus optimal cost, which we know in this case from Seidel, and it's like really a very nice curve. So that's a log scale here, okay, and that's a linear scale here. So you see exponential convergence, linear scale, log scale, and then it jumps down to machine precision. So always look the same in the example. So my second test sequence was more interesting because now the question is, how about the curse of dimension? I mean, now I needed 7,000 iterations, but will I need 10 to the 23 iterations when I go to a larger system, right? So now I go up to 10 to the 31 unknowns, and I increase the number of electrons here, 5, 10, 15, 20, 25, 30. And I want to explain how we increase them because it's physically important. We wanted to take a thermodynamic limit. So you increase the size of the domain and the number of electrons at the same time to keep the amount of volume per particle the same, just as in a thermodynamic limit. So that's a fair test, actually. And so I took here the uniform density. And so, here's what you get. So still converges nicely, and still is a convergence plot we don't need to discuss, but that's the plot I wanted to show. So, so the total number of columns or configurations, they're called columns because each extra configuration in the active set gives you another column in the constraint matrix. That's why it's called that. So it's not the number of, so it's really the number of micro iterations I count. How many new configurations do I have to sample? So that's here, and this is the so this is the number of electrons. This is the total number of configurations sampled, and that's a log plot. And that's a straight line with a small slope. So that so we were extremely happy by this. So this is the size of the state space, and this is the part of it you touch. So it's a tiny, 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 tiny fraction of the state space you touch. And so people who work in wave function methods, they might be familiar with FCI QMC by Ali Alavi and co-workers, where you do a kind of genetic algorithm on CI coefficients. At the end of the day, Ali needs something like, he needs to touch a positive percentage of the whole configuration space in his code. And here, that's a tiny, tiny, tiny fraction. Okay, so it's really nice performance. So I also wanted to explain briefly the connection with classical column generation. So in our context, it would be, we have the same update of primal and dual cell solution, but the update of the subset is different. So in classical column generation, which comes from discrete optimization, you update as follows. You solve a so-called pricing problem, namely you find the configuration that minimizes this expression here, okay? And so you don't just make this, so we just want to make this term negative. We want to find any configuration that makes this term negative. In the pricing problem, you have to minimize it. But that's bad because you're minimizing a high-dimensional function, which is the whole thing you want to do. So by the time you've minimized your high-dimensional function, you might have solved the whole problem. And actually, we proved that this problem is NP complete, even for symmetric multi-marginal optimal transfer with pairwise cost. Okay, so this pricing problem is not good. Actually, related work on the completeness, independent from us, was done recently by Altschuler and Boas. Very nice work, so they have similar results on the NP completeness. And so the combination of genetic candidate generation and then acceptance at a kind of pretty minimal criterion, as long as this thing becomes negative, is is a crude approximation to the pricing problem, and that's kind of what beats the Cursor dimension. So I should say, so among all the current R's inside, this thing is always non-negative, so that's the constraint, that's the dual constraint. So the dual constraint is then that if you plug any of the configurations in the current set omega in, then this quantity is non-negative. So you do make a gain, so you lower the cost by this criterion. Okay, so that's kind of the right thing to do here. So yeah, something in 2D, I just show some examples. We haven't published these because we are pushing them to a larger machine at the moment and want to see how far we go. So this is all done with MATLAB on a laptop. So yeah, pushing it to larger team. But I want to show it here. So some example of 2D. So with the Gaussian density. So here I cannot show the configurations, but I show the Kantorovich potential. So this is 10 to the 33 configurations, 1,000 iterations, 3,000, 8,000, 12,000, 20,000, and after 45,000, it's converged. Okay, 45,000 may look a lot, but the configuration space has size 10 to the 33. And so we also know from theory that the ground state, it's like an inhomogeneous Wegener crystal type thing. So there are only 400 active configurations because I have 20, but times 20 equals 400 constraints. And so these are 3 of them. The others look similar. Okay, but we believe these are optimal. Now, I also wanted to do a test. So this also has interesting applications to data science. So I went back to the Wasserstein Barry Center, this joint work with my recent graduate student, Max Penke at TUM. So we looked at the MNIST handwritten digits, so for handwriting recognition, etc. And so we tried to do the Barry Center of these digits. So the MNIST digits are 28 times 28, so it's 784 grid points for each image. These are small data sets. But okay, then we took 10 of them, then we have 10 to the 28 unknown, so we can do it on the laptop. And so what Max found last week or 2 weeks ago, but we have a good draft and should be on Archive soon. So you get a very nice barycenter of these digits. And so it so happens that in the Wasserstein barycenter case, there is another method for computing the barycenter, which is not the optimal plan, but just a push forward, which is kind of a just a measure on R2. But for that, you need to do smoothing. It's the synchron algorithm, and you can reformulate this for this particular cost only. You can reformulate as a coupled 2 marginal problem, and then what you find is this picture here, and it's much more blurred and smeared out. But you don't get it better than that with the synchron. It turns out the GenCol is really much more accurate. And in fact, when you do the theory, you find it gains so also the grid is finer that you automatically get, because when you compute the multi-marginal plan and then project, it doesn't project onto the same grid points you had, but it gives you 100 times finer grid. And you don't need to smoothen anything. So for example, the 1 here looks, it's a superposition of some tilted ones and untilted ones. But yeah, some people write the ones like this, some like this. And here you get a superposition. That's a really clear line. Okay, so I think it will have nice applications in data science. And I'm happy about that because people always complain, oh, you are so boring. You do electronic structure and all these physics problems. Why don't you work in data science? That's the future. And so it's nice to show people in data science that we also work on hard problems, and sometimes our methods are pretty sophisticated when we apply them to their problems. So yeah, so now conclusions, time to sum up. So this new algorithm is simpler, more accurate, and much faster than previous methods. Computes not just the endpoint density, but also the Kantorovich potential. This was important to us because that is good for use in current and future combinations of Kohn-Sham with SCE, because now there is a reasonable algorithm that computes you this Kohn-Sham potential, and then you can contemplate maybe hybrids that are based on the potential, so potential functional theory or whatever. And okay, based on sparsity of the exact solutions, that's optimal transfer theory on column generation and genetic learning. So that's what I wanted to say. Yeah, thanks for your attention.